Let's now look at an approximation for the Dutch roll eigenvalues. So there's a traditional approximation that we're going to talk about here that's actually not very good. But to understand this, we have to first understand that Dutch roll is a combination of three major things. So we have some roll, some yaw, and some side slip. Okay, all three of these things are acting together. So it's, again, this is this fishtailing feeling, but it's coupled roll, yaw, and side slip. And the traditional approximation actually neglects the roll, okay? And by so doing also neglects any dependency on bank angle. Okay, so this is the traditional approximation, and if you do that, if you use these linearized equations, which we've developed previously, so this is the general eigenproblem that we're looking at. If you neglect the dependency on roll and bank angle, and then do that throughout here. So, for example, we'd neglect the rolling terms here. Anyway, you can whittle this down so that you're left with only four terms here. So we have the cy beta, the cn beta, so that's the dependency on side slip. We have this term here that's dependent on yaw rate, so we've got the side slip and the yaw in there. And then the components in this matrix that correspond are these, so it depends on the inertia about the z-axis here, as well as this this ratio there. So anyway, if you do that, you're left with this 2x2 system that then depends only on, so let's see, let's knock these guys out. What we're left with here is this chi r bar and chi beta. And so you can solve this system analytically to find the eigenvalues. Well, it turns out that this entire approach is not very good. And so we're going to back up here and erase all of this. And we're going to actually discuss an approach suggested by Warren Phillips. This was a publication in the year 2000 in the Journal of Aircraft, and I'll put a link to that article in the description below. But and he also has this in his book, in his flight mechanics book. So you can go either place to find this. And I'm not going to go through the entire development. It's actually fairly involved. It took quite a bit of work for him to work through this and come up with a better approximation. He starts off with these same linearized lateral equations here, so the same eigenproblem, and really picks apart each of the terms in here, deciding whether or not they should remain or be neglected, and has to make some approximations, use some Taylor series. And anyway, it's a fairly involved approach. But a couple of the approximations I just want to point out here in his development, he uses theta equals 0, so he looks at steady level flight, right? So he's going to assume that this is, that should be a 1. So cosine of theta is 1. So theta equals 0 is one of his approximations. So we're looking at wings. Sorry, not bank angle equals 0, although I'm fairly certain that's built into this as well. But for the equilibrium condition, right? But the aircraft does not have a nose up attitude, so theta equals 0, right? That's our elevation angle. So if you do that, then the tangent is 0, the secant goes to 1, cosine goes to 1, and anyway, so that's that approximation. And then he also says that cy comma p bar is small, so we're going to neglect that as well. So cy p bar is this term right there. So we neglect that, and then also the off-axis inertia. So this is the RxZ term. So even for a symmetric aircraft, we're going to have some xz component of inertia, and he neglects that, saying that that's probably small compared to the inertia about the x and z axes. So these two, the diagonal terms here. Okay, so those are a few of the approximations. Again, I'm not going to go through his development. It's rather involved, but I've rewritten his solution in I guess my own my own form here. So he has it in a slightly different form, but I've rearranged it and put it into this form here. So this is this top term here is the dimensionless eigenvalues. And all I've done here is said that the dimensionless eigenvalue is some ratio here that makes it dimensionless multiplied by the dimensional damping rate and damped natural frequency. And the sub dr here stands for Dutch roll. Okay, so this is the damping rate, the Dutch roll damping rate. And again, this is an approximation, and the damped natural frequency approximation. And you can see that it depends on a bunch of our coefficients that we include side slip, roll, yaw, and roll in there. So we've got roll, yaw, and side slip dependency all throughout here. So he also introduces this Dutch roll stability ratio. And anyway, it's also kind of a complicated ratio, but it shows up a couple different places here. So we've got this stability ratio in our frequency as well as in the damping term up here. Okay, so this is what I use for for a closed form solution for the dimensionless eigenvalues or also the dimensional sigma or omega here. So anyway, this should be a fairly good approximation, and he shows in his paper and in his book that it actually is a fairly good approximation, much better than the traditional approximation over a wider range of aircraft designs.